In the previous lecture, we introduced the Big Bang, our model to explain the observed fact of the expanding universe. In today's lecture, we are now going to examine observational tests of the Big Bang model. The universe we see around us today is cold, dark, and very low density. We see hundreds of billions of galaxies out to billions of light years away from us in all directions, and darkness in between. Our universe is very thin and very transparent in terms of its distribution of matter. But it wasn't always this way. The universe began expanding a finite time ago from a very dense, very hot initial state that we call the Big Bang. It is dense in the sense that matter and photons are packed very close together during these early epochs, and it is hot in the sense that photons have very high energies and all of the gas particles have very fast random motions. By all measures, the temperature is very, very high. As the universe expands away from this hot initial dense state, it becomes progressively lower density and colder until we see the low density, cold, dark universe that we see around us today. What are the observational evidences for this Big Bang model? The first evidence for the Big Bang, number one, is that the sky is dark at night. This is a very basic observation that when there's no sunlight in the sky and we're out in deep space, we see a largely transparent universe that is mostly darkness, scattered with little spots of light, all of the stars and galaxies that are the glowing bits of matter in the universe. If the age of the universe is approximately the Hubble time, measured as 1 over the Hubble constant, then light from stars that is farther away than the speed of light times the Hubble time, c over h naught, will not have had time to reach us yet. Even if the universe was infinite and filled with an infinity of stars, because the universe is a finite age, we can only see out to those stars that are as far away as light has had time to travel since the beginning of the Big Bang. As a consequence, the sky should be dark at night. We see this dark night sky today only sparsely filled with stars and galaxies. This is the first bit of observational evidence that the Big Bang is a correct description of our expanding universe. Evidence for the Big Bang number two is that redshift is proportional to distance. We see a Hubble law, that the apparent radial velocity of galaxies is proportional to the Hubble constant times the distance of a galaxy, with the current value of the Hubble constant being about 68 plus or minus 1 kilometers per second per megaparsecs. The more distant a galaxy is, the greater its redshift, the faster it appears to be moving away from us. As we described in previous lectures, this is a consequence of the general expansion of space-time as the universe gets larger and larger, carrying galaxies apart, showing us the Hubble law that is observed for all objects at large distances in the universe. Evidence for the Big Bang number three. The estimate of the age of the universe from the Hubble time is older than the oldest stars. Our current best estimates of the age of the universe, measured from a combination of the Hubble constant, the current day rate of expansion of the universe, and the mass energy density, omega naught, the amount of matter and energy in the universe today, is that the Big Bang, this current phase of expansion of the universe, began 13.798 plus or minus 0.037 gigayears ago. Further corroborated is the fact that this age is older than the oldest stars that we see through the universe. The oldest stars and globular clusters are approximately 13 billion years old, for example, as being derived from the shape of the Hertzsprung-Russell diagram for a globular cluster like M15, where the age of this globular cluster is approximately 13 billion years old. At no place in the universe have we ever found convincing evidence of stars or objects that are older than the universe. This would either be a logical inconsistency or evidence that the expansion phase that we're in now began late in the age of the universe. And so, evidence number three is the universe is older than the oldest of its contents that we can see. These three are not the only tests, nor are they necessarily the strongest tests that we have. Among these three, the fact that the redshift is proportional to distance, the universe shows a Hubble law for the motions of galaxies, is considered a very strong piece of evidence for an expanding universe defined by the Big Bang theory. There are other evidences as well. If the universe were in a very hot, very dense state approximately 13.8 billion years ago, what evidence of this hot initial state is observable today? There are two consequences we're going to concentrate on. The first line of evidence is that if it were hot and dense enough for nuclear fusion to occur, then we should see the products of this primordial nucleosynthesis remaining in the universe around us. The second test we can apply is that a hot, dense, early universe at some point would have been opaque to light. This would have resulted in the production of a cosmic background of light that should still be visible, if faintly, in the universe today. Here are two pieces of potential observational evidence that would point to not that the universe is expanding, but that the universe is expanding away from a very hot, very dense initial state. There may be other ways to explain the expansion of the universe that doesn't require a Big Bang, and indeed many people have come up with different models to try to explain that. But do we see evidence of a hot initial state? These are the questions we're going to turn to next. We'll start with a basic observation. The Sun formed approximately 4.6 billion years ago, about 9 billion years after the Big Bang. By Big Bang, we mean the start of universal expansion as estimated through the Hubble constant and the density parameter at about 13.8 billion years. If we look at the metal content of the Sun, we see that the Sun contains about 28% helium and about 2% metals. All of this is gas that must have been recycled from earlier generations of stars. This gas has been steadily enriched by the products of stellar nucleosynthesis, the production of helium from the fusion of hydrogen, and the production of heavy elements inside of massive stars from the fusion of progressively heavier and heavier nuclei up to iron and nickel, and then spread into the interstellar medium through supernova explosions. The very first stars that we see in the universe are very, very distant from us. They were formed approximately 500 million years after the Big Bang. These first generation of stars contain no recycled gas because they were formed out of whatever the raw gas was that came out of the hot initial dense state. These objects are very far away. Here's a picture of a candidate for one of the most distant star-forming galaxies we've found to date. It's called, rather interestingly named, Z8 under GND under 5296. It's a catalog designation in a project that's designed to try to find these extremely rare objects. It exists at a redshift of about 7.51. At the time that this particular galaxy has begun forming stars, the universe was only about 500 million years old as measured from the time of the start of the Big Bang. However, even this gas contains at least 23% helium, and the most primordial, the most pristine gas we can find in intergalactic space still contains a large amount of helium with traces of deuterium and lithium. This leads to a very surprising result. The very first stars in the universe formed from gas with about 23% helium already. The Sun now contains 28% helium, and so at least after 9 billion years of forming stars, the universe has only been able to augment the content of helium in the universe by about 5%. So how does it start out at 23% if after 9 billion years of star formation, you only get another 5%? What's going on? A different way of asking that question is, how did this primordial or pre-star helium, deuterium, and lithium get made? The universe starts out in a very hot, very dense state and then cools off very rapidly as it expands. If we trace the expansion backwards, what we find is before the universe was about 3 minutes old, so 3 minutes and less in the universe's age, it is going to be too hot for stable nuclei to form. If you form an atomic nucleus by fusion, it's going to as quickly come apart by fission as it forms, and so there's no chance of you finding any stable nuclei anywhere. Go back even earlier, not even forms of recognizable matter exist. It's so hot not even protons and neutrons exist. But in this period of about 3 minutes, there's a brief window during which the universe is filled with a sea of free protons, free neutrons, electrons, and high-energy photons. There are no atoms and there are no complex nuclei, just subatomic particles and photons. After 15 minutes, the universe has continued to expand and continues to cool. By the time the universe is 15 minutes old, it's too cold for nuclear fusion to occur outside of the cores of stars. The universe is simply not hot enough anymore for fusion to occur. Fusion only happens at relatively high temperatures. As a consequence, there is a roughly 10 to 12 minute window during the earliest stages of the Big Bang during which it's possible for fusion to occur. We call this primordial nucleosynthesis. This is a very brief epoch, 10 or 12 minutes long, during which it is possible to build heavier elements from elementary particles like protons and neutrons. Think of it as a Goldilocks problem. Before 3 minutes, it's too hot. After 15 minutes, it's too cold. But between about 3 and 15 minutes, for about 10 or 12 minutes, the conditions are just right for fusion to occur and for heavy elements to be built out of hydrogen, out of protons and neutrons. Primordial nucleosynthesis, however, is very different than the nucleosynthesis we learned about in stars back in Unit 2. And the reason is because of the presence of free neutrons in the hot early universe. We haven't talked about this before, but free neutrons turn out to be unstable outside of atomic nuclei. If I had a jar full of free neutrons sitting out here in the room, it would a neutron would on average decay into a proton, an electron, and an electron antineutrino. The electron antineutrino just takes care of conservation of angular momentum and a little bit of conservation of mass in the process. The half-life of a free neutron is only 10 minutes long. If I had a jar of neutrons coming, for example, out of a neutron collider experiment, and I could find them inside of a bottle of some kind, and I started out with, say, 100,000 neutrons inside this bottle, I wait 10 minutes after I injected the neutrons in there, and half of the neutrons would be gone. There would be only 50,000 neutrons. Another 10 minutes later, half of those would be gone, and I'd be left with 25,000 neutrons, and so on and so forth. In a very short amount of time, all of the neutrons would have decayed into protons, electrons, and electron antineutrinos. However, during the first few minutes of the Big Bang, the universe is not old enough for most of the neutrons to have decayed away into protons, electrons, and neutrinos. And therefore, during this brief 10-minute window, the universe is actually quite rich in free neutrons. In fact, there are so many free neutrons, about 1 for every 5 protons, that it enables a unique situation in which neutron fusion reactions can occur. This is critical for being able to do significant amounts of nuclear fusion during the very brief 10-minute or so window during which the universe is not too hot for nuclei to be stable and not so cold that fusion can no longer occur. Let's see how this works. Primordial nucleosynthesis works by forming helium with traces of deuterium-lithium before it gets too cold to continue. This fusion is unlike the fusion we see inside stars because it's not proton-proton fusion, but proton-neutron and neutron-nuclei fusion. Let's see how this works. The most basic reaction, initially, is that you have a sea of protons and neutrons, electrons, and photons. When it gets cool enough for a neutron and a proton to fuse together to form deuterium, heavy hydrogen, an atomic nucleus containing a neutron and a proton. Because the neutron has no charge, it isn't resisted fusing with the proton. If I try to push 2 protons together, their common positive charge strongly resists those protons fusing together. I have to have very high energies and very high densities for it to occur, and these reactions are very slow. That's why the proton-proton chain is such a slow fusion reaction and only occurs in the cores of stars. But if I have neutrons around, a neutron and a proton can very readily fuse. A neutron and proton fuses into a deuterium. The mass of the deuterium is less than the combined mass of the neutron and proton, and so the difference in mass is turned into a photon. It emits a gamma ray. So I fuse neutrons and protons into deuterium, a heavy isotope of hydrogen, and the creation of a photon. Once I formed the deuterium could then fuse with a second neutron to form tritium, an even heavier isotope of hydrogen consisting of 1 proton and 2 neutrons in the nucleus. This nucleus also emits a photon, a gamma ray, because the mass of the tritium isotope is less than the combined mass of deuterium plus a neutron. Now, it turns out that a tritium has one neutron too many and is radioactively unstable and would eventually decay into helium-3, a light nucleus of helium. But the half-life of tritium is about 13 minutes, so the universe hasn't been around long enough for tritium to have significantly decayed. Besides, the fact that there's tritium there, and there's lots of neutrons and protons, means that tritium can combine with a proton to form helium-4, normal nucleus of very tightly bound helium with the emission of a photon. The mass of tritium plus a proton makes a helium-4 plus a photon, because the helium-4 has a lower mass than the combined mass of a tritium and a proton. This now gives us two of the products we expect from primordial nucleosynthesis. There's a long chain of three reactions that ends with two protons and two neutrons being fused into a helium nucleus, a nucleus consisting of two bound protons and two bound neutrons. There is a secondary side reaction in which some of the tritium collides with some of the helium that's formed late in the process, forming a nucleus of lithium. Lithium is a nucleus with 3 protons and 4 neutrons down inside of it, and since the mass of tritium plus helium is less than the mass of a lithium-7 nucleus, it too emits a photon. This reaction continues until the universe cools down so much that the fusion reactions stop. These fusion reactions are relatively temperature sensitive. If they're too hot, if I form a neutron and a proton into a deuterium, a photon collides with that deuterium when it's formed and has sufficient energy to break it back up into a neutron and proton. Only when the temperature drops and the photons that are running around are too low energy to cause the deuterium to break apart into protons and neutron does the deuterium stick around long enough to find a neutron to make tritium, and similarly the tritium stays around long enough to find a proton to make helium. The outcome, the basic bottom line, is that this neutron-mediated fusion that occurs during this 10-minute window between when the universe was 3 minutes old and about 15 minutes old forms a small amount of deuterium, a whole bunch of helium, which is a very stable nucleus, and a tiny amount of lithium-7 before the universe cools down so much that all the fusion just stops. Therefore, we now have evidence for the Big Bang number 4. The predictions of Big Bang nucleosynthesis agree very strongly with observations. The predictions are that we should expect to see a ratio of helium to hydrogen coming out of the Big Bang between 20 and 26%, and a ratio of deuterium to hydrogen between 1/10,000th of a percent and 0.1%. And indeed, the observations are that the primordial abundance of helium, the most pristine gas that we find, is between 22 and 24% helium relative to hydrogen, and the primordial abundance of deuterium, the ratio of heavy hydrogen to regular hydrogen, a single proton surrounded by a single electron, is between 0.001 and 0.02%. This diagram over here on the right-hand side of the screen is a detailed set of model predictions for what you would expect for different models with different amounts of matter and photon density in the early universe. What matters for when nucleosynthesis begins and ends is what the density of matter is relative to the density of high-energy photons. Too many high-energy photons around, and those photons can break up the nuclei before they can form. Too few high-energy photons around, you get less breakdown and more fusion can occur before the temperature in the universe drops to the point that all the fusion stops. It's kind of a delicate balance, but nonetheless, we don't know exactly what the density of matter and the density of photons were in the early universe, but if we look at the predictions of primordial nucleosynthesis, if that was the primary guiding light, then we would expect the abundances of helium-4, the normal nucleus of helium, deuterium, light helium or helium-3, and lithium-7 should all line up on a line close to where our estimates of the matter and photon density are, and indeed, those predictions and the observations are right in line with each other. The predictions of Big Bang nucleosynthesis very strongly agree with observations, telling us that this hot, early phases in which nucleosynthesis occurred have left behind observable products in our current-day universe.